I want to illustrate now the different vibrations at the example of the molecule acetyl phosphate. We have computed the vibrations of this molecule because it is a model compound for the phosphorylated form of the amino acid aspartic acid. The first short movie gives an overview of the molecule. It consists from left to right of a phosphate group, a carbonyl group, and a methyl group. This video shows one of the stretching vibrations of the methyl group. All bond lengths elongate at the same time and contract at the same time. Therefore, this vibration is called symmetric stretching vibration. It should be noted that the movements are largely exaggerated. In reality, the bond length changes are much smaller. As we have 3 CH bonds in the methyl group, we expect 3 stretching vibrations. The other 2 are shown in the following. This is an example for an asymmetric stretching vibration. Different bonds contract and elongate at the same time. Therefore, this vibration is called asymmetric stretching vibration. Asymmetric means simply not symmetric. If we ignore the CH bond that points upwards because it moves very little, we see that the 2 remaining bonds do exactly the opposite. While one is contracting, the other one is expanding, and vice versa. Such a vibration is called antisymmetric vibration. Note the difference between asymmetric and antisymmetric. Asymmetric means just not symmetric, whereas antisymmetric means that one bond behaves in exactly the opposite way as the other bond. Finally, this is the last stretching vibration of the methyl group. Again, it is an asymmetric stretching vibration. The next example is a bending vibration, again of the methyl group. The C-CH angle oscillates, and it does so in the same way for all hydrogen atoms. Therefore, this vibration is a symmetric bending vibration. There are also asymmetric bending vibrations, but I will not show them. Instead, I want to show this bending vibration, where the angle of the POC group oscillates, which makes the 2 ends of the molecule move relative to each other. Finally, I want to show two examples of torsional vibrations. In the first one, the methyl group rotates against the rest of the molecule, which changes the dihedral angle between the methyl group and the carbonyl group. Show it again. In the second example, the carbonyl group rotates with respect to the rest of the molecule, which changes the dihedral angle between the carbonyl group and the other 2 groups. In the above examples, vibrations were shown which involved just a small number of atoms in the molecule. However, it is quite common that many, if not all atoms move in a vibration. An example is shown in the next movie. It is clear that this vibration involves all atoms of the molecule and many internal coordinates change. However, there is some order in this complicated movement. All internal coordinates vibrate with the same frequency, they go through their equilibrium positions at the same time, and they adopt either the minimum or the maximum value at the same time. This brings us to the concept of normal modes, which will be explained next.